Number 51. For the following exercises, graph the polynomial functions using a calculator. Based on the graph, determine the intercepts and the end behavior. Okay, so we have f of x equals x cubed times the quantity x minus 2. Okay, now this has end behavior similar to x cubed times x, or x to the fourth, for large absolute value of x values. Alright? In other words, what I'm saying is, for large absolute value of x, this is going to look a lot like x cubed times x. Forget about the minus 2, because when x is very big, an absolute value, it's going to overwhelm that little bitty minus 2. Alright? That could be minus a billion if you want, and I can still say the same thing. X could be 10,000 million, 10 quadrillion, whatever you want it to be, much bigger than this, whatever it is. Alright, x will eventually get bigger than this in absolute value, bigger than this, that is, that constant there. And so then it will be overwhelming that minus whatever that is, alright, that constant. And so, again, for a large absolute value of x, then it's going to look like x to the fourth, alright? So, so we can predict the end behavior without drawing the graph. As x goes to plus or minus infinity, then f of x goes to positive infinity. Okay? And the intercepts are 0, 0, 2, 0. I'm putting those down. I got those off of the graph, alright, which is what they instructed us to do. And I'm just putting that there ahead of time. But here's the graph that I drew on my computer. And there you go. Number 53, we have f of x is equal to x times the quantity 14 minus 2x times the quantity 10 minus 2x. Alright, so we can predict the end behavior without graphing it. It's going to, for large absolute value of x, it's going to have behavior, end behavior that is, similar to x times negative 2x times negative 2x. So as the absolute value of x gets huge, alright, these constants are really going to be dwarfed by these terms here, alright. So they're not going to contribute much to the graph, so it will begin to look a lot like this graph here, or this function. Okay, if you simplify this, you get 4x cubed. So it will look like y equals 4x cubed as the absolute value of x gets very big. All right. So as x goes to negative infinity, f of x goes to negative infinity. And as x goes to positive infinity, f of x goes to positive infinity. And the graph will bear this out. Also, the intercepts from the graph, which I graphed and then I got the intercepts, are 0, 0, 5, 0, and 7, 0. So you can see these on the graph as well as the end behavior right here. '55. We have f of x equal to x cubed minus 16x. So the dominant term here is x cubed. All right, it's for large absolute value of x. This term is going to be a lot bigger than this one. All right, so it will dominate the whole function. So it's going to look a lot like y equals x cubed for a large absolute value of x. Okay, so you can determine end behavior as x goes to negative infinity, f of x goes to negative infinity. And as x goes to positive infinity, f of x goes to positive infinity. All right. Also, we have intercepts that I got off of the graph. Negative 4, 0, 0, 0, and 4, 0. Alright, so let's look at the graph. Okay, number 57, we have f of x equals x to the fourth minus 81. Okay, clearly the dominant term is x to the fourth. So for large absolute value of x, this term is going to overwhelm the minus 81. All right, so the behavior of the function will look like y equals x to the fourth as absolute value of x gets large. Alright. Instead of saying absolute value of x gets large, I could say as x gets large or gets very small, if you want to think of negative numbers as being small. That's kind of awkward to say that. You know, you've got two things you have to say. In other words, as x goes to the left on the number line really far, or as x goes to the right on the number line really far, then it starts to look like y equals x to the fourth. So instead of saying all that, I just say as the absolute value of x gets large. So if x is negative 1,000,000, you can't really call that large, right? Because it's a negative number. It seems kind of strange to say that's large, because positive 1,000,000 is large compared to negative 1,000,000. So if you take the absolute value of that, whether it's negative 1,000,000 or positive 1,000,000, the absolute value is big, right? It's going to be 1,000,000. So it's a lot easier to say as the absolute value of x gets large. Okay, that sounds kind of awkward probably the first time you hear that, but it does simplify things somewhat. All right, so it's going to look like this as absolute value of x gets large. All right, so as x goes to plus or minus infinity, so I put plus or minus because f of x is going to go to positive infinity no matter what, so I just put it all in one line here. F of x goes to positive infinity, whether x is positive or negative. All right, it's an absolute value of x gets large. All right. Okay, so the intercepts from the graph are -3, 0, 0, -81, and 3, 0. So here is a look at the graph. Okay, number 59. F of x is equal to x cubed minus 2x squared minus 15x. So the dominant term would be x cubed. It's got the highest power. And as the absolute value of x gets large, this term will overwhelm the other two terms. All right, it will be a lot bigger in absolute value. All right, so it's going to look like y equals x cubed as x goes to minus infinity or positive infinity. All right, so as x goes to negative infinity, f of x goes to negative infinity. And as x goes to positive infinity, f of x goes to positive infinity. All right. And the intercepts are -3, 0, 0, 0, and 5, 0. Got those off of the graph. So let's look at the graph. Number 61. For the following exercises, use the information about the graph of a polynomial function to determine the function. Assume the leading coefficient is 1 or -1. There may be more than one correct answer. So the y-intercept is 0, -4. Let me write that down. 0, -4. The x-intercepts are -2, 0 and 2, 0. The degree is 2. So we have a quadratic function. All right, and behavior we have as x goes to negative infinity, f of x goes to infinity, and as x goes to infinity, f of x goes to infinity. All right. So the polynomial is of degree 2, leading coefficient is plus or minus 1. So that means that f of x, so far, as we can determine, is equal to ax squared plus bx plus some constant, ax squared plus bx plus c. And we know that the leading coefficient is either 1 or -1, so a is the leading coefficient. A must be plus or minus 1. Alright? So this is a quadratic function of degree 2, and a is a leading coefficient plus or minus 1. That's what we know so far. Now you take the intercepts. Alright? That gives us some crucial information. The y-intercept is 0, -4. That means when x is 0, y equals -4. Okay? So that means that f of 0, when x equals 0, will give you just the constant, right? 0 squared times a will be 0, 0 times b will be 0, and that's what you have left, so that must equal -4. Okay, so that means that f of x is ax squared plus bx minus a 4. So in other words, the constant term of this function, this quadratic function, is -4. Okay. Now the x-intercepts are -2, 0, and 2, 0. Alright, so for that to be the case, then f of x must equal a, that's the leading coefficient, times x plus 2, x minus 2. Alright, that gives us a quadratic when you multiply these out. A is either plus or minus 1, and these have roots of plus or minus 2, just like we see here, right? They gave us that information. So you multiply this out, multiply these two binomials, and you get a. X plus 2 times x minus 2 is x squared minus 4. Distribute the a through, you get ax squared minus 4a. Alright? But we already determined that the constant term is -4, and that's the constant term. This is a constant because a is a constant, alright? It's not a variable. And -4 is definitely a constant. So a equals 1. Therefore, a equals 1. Alright? And that falls in line with what they told us. A must be plus or minus 1. So, we can finally conclude that f of x is equal to x squared minus 4. Alright. Number 63, we have the y-intercept is 0, 0. And x-intercepts are 0, 0, and 2, 0. Degree is 3. And the end behavior as x goes to -infinity, f of x goes to -infinity, and as x goes to infinity, we have f of x going to infinity. Now, we'll use the fact that it's a degree 3 to come up with a general form for this polynomial. It's degree 3, so f of x must equal ax cubed plus bx squared plus cx plus d. Now if you use the general form given in most books, including our book, you could write a sub 3x cubed, blah blah blah. Use a's instead of a, b, c, d, but it gets a little bit cumbersome. Alright, so and this isn't really a big polynomial, so I'll just stick with a, b, c, d. Alright, and we all understand what they mean. These a, b, c, and d are constants. Alright, and a has to be plus or minus 1 according to the general directions that were given. Alright, use the intercepts now to get a little bit more specific. We have y-intercept is 0, 0. Okay, so f of 0 is 0. Alright, so when you plug in x equal to 0, that's going to become 0, that term's going to become 0, that term's 0, and then you have just d left. So in order for f of 0 to equal 0, then d must be 0. Alright, so d equals 0. So now we know so far that f of x equals ax cubed plus bx squared plus cx. Alright, now use the x-intercepts. We have 0, 0 and 2, 0. Okay, so therefore f of x must look like this. You've got the leading coefficient a, and then you can have x squared, x minus 2. Alright, this, when you let x equal 2, this becomes 0 and the whole thing becomes 0. Alright, and for this, when you let x equal 0, the whole thing becomes 0. Okay, because that's 0. So why is it squared? Because this is degree 3 polynomial. If it was degree 2, you could say it's just x. And when you multiply these out, you'll get the x squared. Well, but it's a degree 3, which they told us, so when you have x squared times the x, you're going to get the x cubed. Okay, so let's multiply that out, distribute the ax squared through, and you're going to get ax cubed minus 2ax squared. Alright, now the end behavior will give us a little more information. We didn't really use it in the last one, but here use this fact. As x goes to negative infinity, then f of x goes to negative infinity. Okay, so as x becomes more and more to the goes more and more to the left on the number line on the x-axis, all right, negative numbers. This when you cube it, you get a negative, all right, and when you square it, you get a positive. Okay, so what does, if a was a negative 1, this would become a positive term, and it's the dominant term. All right, and f of x would go to positive infinity. So what this tells you is that as x becomes in absolute value greater and greater, going to the left on the x-axis, this has to be a positive 1. All right, we know it's either plus or minus 1. So it can't be a minus because the minus will make that a positive term, and again, this is the dominant term, and it's going to be positive, and it's going to overwhelm whatever this is. All right, so we know that a must be positive 1. Okay, so therefore f of x is equal to x cubed minus 2x squared. Just let a equal 1. X cubed minus 2x squared in this here. Just let a equal 1 there and there. And there you go. Now, the book's answer is a little bit different from mine. All right, the book's answer is x cubed minus 4x squared plus 4x. This happens to work with these conditions. All right, so I'm saying that my answer is better because it's simpler. All right, so the simplest answer wins the competition, in my opinion. All right. However, the book's answer does work, and what I've done is I've graphed both answers, and my answer appears as the red graph. The book's answer is the black graph, and you can see that they have the same x and y intercepts. All right. In fact, they look practically the same, except one is shifted. However, there are the same x and y intercepts. So both of them work, and they have the same end behavior as well. Again, mine is red and the book is black. So take your pick. I choose the simpler one, but I guess in this book it doesn't really matter. Okay. Number 65, we have a y-intercept at 0, 1. No x-intercepts. So in other words, it never touches the x-axis. All right. The degree is 4. And the end behavior as x goes to negative infinity. In fact, as x goes to either positive or negative infinity, f of x goes to infinity. So I'll say as x goes to plus or minus infinity, f of x goes to infinity. So that encapsulates the end behavior in one line. All right. So it's degree 4. Okay, so f of x must look like this in general. Ax to the 4th plus bx cubed plus cx squared plus dx plus e. Alright, where a is plus or minus 1. Now, before I go further, I need to point out that lowercase e is reserved usually in mathematics for something called Euler's number or Euler's constant. It's a famous number in mathematics, and it's named after the Swiss mathematician, very famous Swiss mathematician named Leonhard Euler. That's spelled E-U-L-E-R. All right, he and Gauss were probably two of the most famous mathematicians who ever lived. So anyway, there's a certain number associated with his name, and it's symbolized by lowercase e. Okay, you'll study about that later. It's coming up soon on logarithmic and exponential functions. All right, and you'll learn about Euler's number. But for now, let's just disregard Euler's number and just say this is the constant term. All right, as long as you and I understand each other, I think we'll be okay. All right, so this is not Euler's number. Okay, all right. So going on here, the y-intercept is 0, 1. So we can find out what Euler's number here is. Haha, just kidding. We can find out what e is here. F of 0, in other words, is equal to 1. So when you plug in x equal to 0, that term becomes 0, that becomes 0, that becomes 0, that becomes 0. All you have left is e, and that must be 1. So e equals 1. All right, so what do we know so far? Therefore, f of x is equal to ax to the 4th plus bx cubed plus cx squared plus dx plus 1. All right. There's no x-intercept. And as I've already said, that means f of x does not equal 0. Therefore, f of x does not equal 0 for all x. This upside down capital A in logic means for all. Alright, so there's also another symbol we use from logic quite often in math. It's a backward uppercase E. That means there exists, or there is. So we use these two symbols quite a lot, borrow that from symbolic logic. And so that means for all x. It's a nice abbreviation. Alright, and it looks cool. And when people look at that, they think you're very intelligent, all right, and they're impressed. So you can use this liberally whenever you can. Anyway, f of x does not equal 0 for all x. No matter what x is, f of x never equals 0. It never touches the x-axis. Remember, y equals f of x. Y will never equal 0. Okay? So, also the end behavior shows that f of x approaches infinity, positive infinity, as x goes either direction, plus or minus infinity. Okay, so if f of x is never equal to 0, it never touches the x-axis, and it approaches positive infinity, then f of x must be greater than 0, or positive, for all x. Alright? Must be positive for all x. So that's about all we can tell from the information they gave us. So what are we going to do? Well, it's got to be a degree 4 function. And what we want to do is obtain the simplest function that will meet these conditions, right? So if you let a equal 1, see, you have choices here. Let a equal 1. Well, you're pretty much you pretty much have to let a equal 1 because that's a dominant term. All right. If it's negative, whatever that is going to be positive, and then negative times positive is negative. So we already determined that f of x is positive for all x. So we have to. I'm not going to let it. It's going to have to be. I'll cross that out. A has to equal 1. All right. And we can let. Here's where let comes in. Let b equal c equal d equals 0. Alright? And that'll give us the simplest such function. Therefore, f of x will equal x to the 4th plus 1. And that does meet our conditions. Okay, number 67. For the following exercises, use the written statements to construct a polynomial function that represents the required information. In other words, word problems. Okay, so we have a cube which has an edge of 3 feet. So you understand that a cube is a three-dimensional version of a square. All the sides are equal. Okay. The edge is increasing at the rate of 2 feet per minute. Express the volume of the cube as a function of m, the number of minutes elapsed. Holy cow! Increasing. We got movement going on here. Okay, well, we can solve this one, no problemo. It's going to take a while though, but we've got, let's draw our cube here. Like I said before, always helps to draw pictures whenever they're applicable on word problems. It helps you to organize your thoughts, if nothing else, and that every little bit helps when you do word problems, alright? So even if it doesn't seem to help much, go ahead and draw the picture. Get into the habit. So each side is 3. 3 feet. Okay. the volume will be length times width times height, 3 times 3 times 3 in this one, and it'll be in cubic feet. And the volume function can be written as a cubic function, all right, V of m. V of m, where m is the number of minutes elapsed. Okay, so the volume as a function of minutes will be cubic, all right. Why? Because the volume will always be in cubic feet. Okay, so am cubed, m is the variable here, am cubed plus bm squared plus cm plus d. All right. Now the initial volume, v of 0, in other words, the starting volume, is this illustrated by that picture, and it's 27. Now v of 0, when m equals 0, all of these terms become 0 except for d, and v of 0 equals 3 times 3 times 3, which is 27. So d must equal 27. All right. Okay, so therefore v of m will equal am cubed plus bm squared plus cm plus 27. Well, alright. That's not much, but it's something. It's better than a blank piece of paper or a blank board, right? So we've got something. We're making progress. Now, how do we handle the cube's growth? How do we do this? Well, we use the fact that the edges are increasing at the rate of 2 feet per minute. Okay, so make a table showing the cube's growth. All right, so I'm going to start with the length m, or not the length m, but the time m in minutes, and then edge length. And then the volume, which will be edge cubed, the edge length cubed. All right. And so at time m equals 0 minutes, the edge length is 3, just like in the picture here, and we already know the volume at that point was 27. Okay. And now, after 1 minute goes by, we add 2 feet. The cube is growing, the edge is increasing 2 feet per minute. So in 1 minute, the edge becomes 5. Each edge, that is, becomes 5. And the volume, which would be edge cubed, is 5 times 5 times 5, or 125. Okay, and then how about when we have 2 minutes go by, then add another 2 feet to 5, you get 7 for each edge, and then cube 7, you get 343 as the volume, 343 cubic feet, and then we need just one more here, 3. The edge length is 9, and the volume is 729. Alright, now what we get from this table are 3 ordered pairs. All right, we're going to use m equals 1, 2, and 3 and get 3 ordered pairs, m, v, capital V, for volume. In other words, the first coordinate is the minutes, second coordinate would be the volume. All right. Why am I using m and v and not edge length? Well, our function is in terms of m here, all right, and it gives us the volume v. So we're dealing with m and v here. So I've got 125, 2, 343, and 3, 729. Alright, I've got those 3 ordered pairs, and we can use these with V of m to form a system of three equations in three unknowns. The unknowns are a, b, and c. All right. So in order for me to set this up, what I'm going to do is first we're going to have three equations using this model. Well, we use this one right here. All right, v of m. We already know it equals this, so we're going to use this. And for the first equation, you let m equal 1 here, here, and here. And then you're going to have, well, 1 cubed, 1 squared, and 1. They're still 1. So you get a plus b plus c equals plus 27 equals 125. All right. So that would be our first equation. The second equation would be you let m equal 2, calculate these values here, and then set it equal to 343, and then you'll have a third equation. All right. So let me erase first so I can get the room. I'm going to need a lot of room for this. So that's what we're going to do next after I erase. So hold on. Okay, we're ready to go here. We have three equations in three unknowns. You first let m equal 1 in v of m, and so we have a times 1 cubed plus b times 1 squared plus c times 1 plus 27 equals, the volume at that point was 125. And then we have a, let m equal 2, a times 2 cubed plus b times 2 squared plus c times 2 plus 27, and the volume when we had 2 minutes go by was 343. One more, let m equal 3, we've got a times 3 cubed plus b times 3 squared plus c times 3 plus 27 equals, and that was 729. So we have a system now of three equations and three unknowns, a, b, and c. All right. So now what we do is we simplify these three equations. So you multiply everything out, simplify, move the constant, the 27, to the left, the right side. All right, subtract 27 from both sides. In other words, do it in all three, and so all you have on the left side would be the a, b, and c terms. All right, so you've got the first one becomes a plus b plus c equals 98. Second one is 8a plus 4b plus 2c equals 316. And the third is 27a plus 9b plus 3c, oops, 3, if you can make that out, 3c, equals 702. Now these last two equations can be simplified. You can divide the first equation on both sides by 2, all right, which is perfectly legitimate. And so I'll draw this double arrow, meaning you can go back and forth, all right? So you've got, dividing both sides by 2, you get 4a plus 2b plus c equals 158. And we can also divide the third equation by 3 on both sides to simplify. and that gives us 9a plus 3b plus c equals 234. Okay, so to make it easy to follow, or as easy as possible to follow, I'm going to label these three equations. Equation 1 encircled, equation 2 in a circle, and equation 3. Alright, so we can keep track of what's going on. So you may not have seen it done this way before, but I found that this method keeps track of what you're doing pretty nicely, and if there's a mistake made, you can always go back and you know exactly what steps you took along the way to get the end result if you label it the way I'm doing. Alright, and then you can you won't spend so much time trying to remember, oh, what did I do here? Oh yeah, because it gets a little complicated. So what I'm going to do is I'm going to pick a variable to eliminate. I'm going to use two of these three equations, alright, and I'm going to choose one of the variables to eliminate. The c's look to be the easiest to eliminate, alright. To eliminate the c's, all I have to do is take, for example, equation 2 rather, and from it subtract equation 1. So that's what I'm indicating right here. Equation 2 minus equation 1. Okay? So let's write equation 2. 4a plus 2b plus c equals 158. And then I'm going to subtract from it the equation 1. A plus b plus c equals 98. Alright, so I've got 4a minus a is 3a. 2b minus b is b. C minus c is 0. 158 minus 98 is 60. So that gives me a new equation in just two unknowns, a and b. I'm going to call that equation 4 in a circle. Alright. Now what I do is I take two other equations and eliminate the c as well. And so what I'm going to end up with is an equation involving just a and b. And so I'll have two equations involving just a and b. And I'll have two equations in just two unknowns. And then I solve that in the usual way. So you can use any two equations you want. I'm going to continue using equation 1, but this time I'll use equation 3 minus equation 1. And that's what I'm putting here, 3 minus 1. Alright. So for equation 3, I've got 9a plus 3b plus c equals 234. And from that I'm subtracting equation 1. So that's a plus b plus c equals 98. Nine a minus a is 8a. 3b minus b is 2b. C minus c is 0. 234 minus 98 is 136. Alright. Now I can divide both sides of this equation by 2 and come up with a simpler equation. Alright, so you divide this equation by 2 on both sides and you get 4a plus b equals 68. So that's going to be my new equation 5. Put that 5 in a circle. There you go. Alright, so I've got equations 4 and 5. I'm going to solve those for a and b. Alright, so however I have to erase again. So hold on a sec while I erase. Okay, here we go. Now I've got equations 4 and 5, and I'm going to take equation 5 and from it subtract equation 4. So we've got equation 5 is 4a plus b equals 68, and subtract from that equation 4, that's 3a plus b, oops, I didn't want to put the closing parentheses just there yet. Okay, 3a plus b equals 60, now close parentheses because I'm subtracting everything from equation 5. Okay, so that's 4a minus 3a is a. What I'm doing is I'm eliminating the b's. That's why I set it up like this, because that would be the easiest thing to eliminate. Alright, so b minus b is 0, and then 68 minus 60 is 8. A equals 8. Alright, now what we can do is substitute a equals 8 in equation 4. Alright, we can use any of the previous equations, but use just the one involving just a and b, because if we have one of these variables, then we know what the other one is. Alright, we can solve for the other one. I'm going to use the equation 4. So let a equal 8 in equation 4. So what we have is 3 times 8 plus b equals 60, and then b must be 36. Alright, now we're going to substitute we need to find a c, so we can use this one of the original equations involving a, b, and c. Use the easiest one, that would be equation 1. Alright, so substitute a equals 8 and b equals 36 in equation 1. Alright, so we've got 8, that's a, plus b, which is 36, plus c is equal to 98. And so that means c equals 54. Alright, so we've got them. So therefore, go back to v of m and let a equal 8, b equal 36, and c equal 54. So this is 8m cubed plus 36m squared plus 54m, and then plus 27, and there is our volume function. Okay, number 69, the last problem. Get ready to run out of this joint. We're going to be done with this pretty quickly too. This one's not going to be too bad. Alright, the last problem. So we have an open box is to be constructed by cutting out square corners of x-inch sides from a piece of cardboard 8 inches by 8 inches and then folding up the sides. Express the volume of the box as a function of x. This Box construction is pretty famous in mathematics. You'll see this same kind of construction in calculus. Alright, a lot of problems are set up using this same construction of a box. Alright, so they're familiarizing you with it now. Okay, so here's our box, or here's a piece of flat cardboard. Drawing a picture. I'm going to cut out corners. Those dotted lines indicate where you cut. Then what you have are tabs on each side. Fold up the tabs, glue the edges together or tape them together somehow, and you end up with a box. Alright, so the length that you start with is 8 inches. And this distance here that distance is x inches, and this distance is also x. Okay, so you're cutting out x by x corners. Alright, so what do you have left? You have 8 minus an x and another x, 8 minus 2x. So that's what you have left here, 8 minus 2x. Alright, that says 8 minus 2x. Okay, same thing on this side. Alright, now when you fold up the box, or when you fold it up so it makes a box, you get a shallow box. Well, it depends on shallow depends on how big x is. Like this, you fold the tabs up. Like that. And this is x. This is 8 minus 2x, and that's 8 minus 2x. Alright? So there's your finished box. Okay? So the volume as a function of x will be x times these two, right? The height times the length times the width. Okay, so x times the quantity 8 minus 2x squared. Okay, and you can square that out. All right, that gives you x times 64 minus 32x plus 4x squared. When you square that out, and then distribute the x through, and then I'm going to arrange the terms in descending powers of x. So you get 4x cubed minus 32x squared plus 64x. And voila, there you go. That is your volume function. Use it wisely, because it's the only one I'm going to do tonight. Well, I guess I've done some other ones tonight, haven't I? And so have you. So, great job. Pat yourself on the back. Either side, both sides if you want. Alright? Good job. Hang in there. We're getting through this stuff, and we will make it to the end. Alright? But for now, take a breather. Alright? I hope you can. I hope you can take a break, put some shrimp on the Barbie, having a beverage of your choice, and I will see you in the next installment. All right, stay tuned, don't touch that dial.